Okay, so today we're going to continue working on Chapter 5, and Chapter 5 is on differential analysis. Okay, whereas in Chapter 4 we dealt with integral analysis. So the stuff we dealt with in Chapter 4 involved, so say we had some goofy object, and through experiments we measured the velocity profile both before and after the object, like so. We're using an adequately sized control volume. We can find bulk information such as the drag force acting on this object here through a properly chosen control volume. Okay, but this analysis that we did, we can only find these bulk properties. We can't find any of the details associated with the fluid flow. So if you're interested not only with the drag force, but with how the fluid is going around the object, and there may be some interesting stuff happening behind where the fluid is swirling around. If you want those kinds of details, then this integral analysis isn't quite up to par. So instead what we have to do a differential analysis. And the big idea of what a differential analysis does is rather than looking at the fluid as one giant control volume, instead we break this region into an infinite number of small control volumes, such as this. So here we're describing a very tiny control volume, and we're going to just pepper spray the entire fluid with a whole bunch of infinitesimal control volumes. Okay, whereas in this big control volume, which we had here, we can only find the total mass or an average density in the control volume. Any difference of say, the density from say 0.1 here, and the density might be different on 0.2, that information is completely lost if we have this big giant control volume over the entire surface. But instead, if we want to know the density of our fluid as a function of position and time, we need to break this domain or break this large control volume into a bunch of tiny little control volumes and then integrate them all up. And so here we can find the density at the center of this control volume, call that 1. We can find another density at the center of that control volume, say 2, and find the density at the center of control volume 3, and so forth. And so you can see that in each of these control volumes we're finding an average density, but if we shrink these control volumes, that has a size, that's of size delta x, or delta y, I should say. And we shrink the size of the control volume to where it is essentially the size of a single point, and we have an infinite number of these infinitely small control volumes. We can find the details of the velocity vector and the density and everything else as a function of position in the entire control volume, and you can find all the little details of the fluid flow. And so how we find these equations is, first we just find a generic control volume that is of infinitesimal in size. So then, and we apply our RTT like we always did. So on Thursday in class, I did conservation of mass, and that's partial t, the integral over the control volume of rho dV, plus the surface integral of the net mass flux out of the control volume. Okay, and so rather than applying it to this big giant control volume that we have here, I'm instead going to apply it to one of these infinitesimally small control volumes here. So I'm going to redraw that here. So we have an infinitesimally small control volume. And the width, I'll just call that delta x, and the height will be delta y. And so what we'll do as the analysis proceeds is we will shrink delta x and delta y and take their limit as they approach 0. Okay, and the center of this control volume is at point x, y, and x will be in the horizontal direction, and y will be in the vertical direction. Okay, and so we need a control volume. So here, we're going to be very careful, and we're going to define the mass flux vectors going through this as rho v dot n hat times the area at x plus delta x over 2. And the reason for doing that is that when we do this type of analysis, we need to keep very careful, we need to very carefully consider where each of these points are. And so this point here at the center of the control volume is at x, y, and the distance between the center of the control volume where we're going to find rho is delta x over 2. So the distance between this point here and that point there is simply delta x over 2. And so that's what this notation here means, is that we are evaluating rho v dot n hat times the area at delta x over 2. And in reality, it is also at position y, but if we're not shifting it, if we're not shifting a coordinate by a delta y over 2 or delta x over 2, we simply, by tradition, we just drop that. Okay, and so here, again, draw the I hat vector like we always did before, and at the center I'm going to do the same thing for the j direction. So this will be rho v dot n hat times the area at y plus delta y over 2, and on the bottom we'll have rho v dot n hat times the area at y minus delta y over 2, and the n hat here is minus j hat. And going in from the right, we'll have rho v dot n hat times the area at x minus delta x over 2, and the n hat vector for this face will be at minus I hat. Okay, so now we go through and do this almost as we did before, but here we're going to take advantage of the fact that the control volume is infinitesimal in size. So what we will wind up doing then is we'll use the midpoint rule. Okay, and so the midpoint rule states that if you want to find the integral of, say, 0 to L of f dx, that is approximately L times the function evaluated at L over 2. Okay, and normally this is, for a typical integral, this is the most crude way that you can do that. So this normally has lots of error. Okay, but as delta x in a control volume goes to 0, or in this case, as L approaches 0, we're just taking a tiny little piece of it. This actually starts to become exact. So in the limit, as L approaches 0, this becomes exact. And so we're going to take advantage of that. So we're going to take advantage of this midpoint rule and the fact that it's exact for an infinitesimal control volume to find these two integrals here. for the conservation of mass. Okay? So, applying the midpoint rule, we have partial t of the volume integral of rho dv. Well, we're going to apply the midpoint rule. So that'll be partial t times an approximation of the volume integral. Well, we're going to use the midpoint rule, so that's just the density evaluated at the center of the control volume, so that's rho x comma y times the volume. Okay, so that would be delta x times delta y and times 1 for the unit depth in the z direction. Okay, and again, as I stated earlier, if a coordinate is not shifted by delta x or delta y, we simply drop it. So I would simply write this as partial t of rho delta x delta y. Okay, and since we're assuming the CV doesn't deform, we can yank out delta x delta y because they're not a function of time. Then this implies that partial t of the volume integral of rho dv equals delta x delta y partial rho partial t. Okay, so we've done the volume term. So now we need the surface integral of the mass flux out. Okay, and I will only do the positive x face in detail. So now need the surface integral of rho v dot n hat dA. So the plus x face plus x face. So I'll just draw that here. So this is a plus x face. It's of height delta y. And the n hat vector is I hat. And we have rho v dot n hat a at x plus delta x over 2. Okay. And so essentially what we're doing here, where I got this from, is we're doing the integral over area, I'll call this area 1, of rho v dot n hat dA while using the midpoint rule. This just becomes rho v dot n hat evaluated at the midpoint, which is delta x over 2, times the area. Okay, and so that's essentially what this means. And the area would be delta y times 1. Okay, because again, we're assuming a unit depth in the z direction. Okay, and the height is 1, so the cross-sectional area of our control volume is just delta y times 1. Okay. And v, if you recall the velocity vector, is equal to ui hat plus vj hat plus wk hat. Well, this is a two-dimensional control volume, so w, there's no 3D components, so this is 2D, so that just goes away. And so v dot n hat equals ui hat plus vj hat dotted with I hat. And so that just equals u. And of course, this is evaluated at x plus delta x over 2. Okay, so now we know v dot n hat, we know rho, we know a. We can put everything together. And then the integral over rho v dot n hat dA equals, again, using the midpoint rule, equals rho u times delta y at x plus delta x over 2, or this equals delta y times rho u at x plus delta x over 2. Okay. So this is almost identical to using the uniform Fourier assumption, but there is some subtle little differences to it. Okay. And same thing, so we apply this to the minus x face, which would be the left face. So here, n hat equals minus I hat, and v equals ui hat plus vj hat, evaluated at x minus delta x over 2, because again, we have shifted from the center of the control volume to the left side, and that's at position x minus delta x over 2. And we do this integral, and we get integral over a2 rho v dot n hat dA. That equals minus delta y times rho u x minus delta x over 2. Okay. And again, we get this because v dot n hat for the left face is equal to minus u at x minus delta x over 2. Okay. And then the plus y face, or the top face, we have integral over that area of rho v dot n hat dA. Well, that's equal to delta x times rho v at y plus delta y over 2. And the reason this comes from the area at y plus delta y over 2. And so here's the top face. This is rho v dot n hat. This is j hat. And this width here is delta x. Okay, and so the cross-sectional area is again just the width times the depth. Which is delta x times 1. Okay. And then minus delta y, which is the bottom. We have the integral over that area of rho v dot n hat dA equals minus delta x times rho v at y minus delta y over 2. Okay. So now, to find the surface integral of rho v dot n hat dA, we just walk around the control volume and add up all of our approximate integrals that we found earlier. This one, and then this one. Okay, so we just add them all up. And so this will equal to the contribution from the left face, so that's delta y, times rho u at x plus delta x over 2, plus the contribution from the left face, which will be minus delta y, rho u at x minus delta x over 2, plus the contribution from the top, so that's plus delta x, rho v at y plus delta y over 2, minus the contribution, or plus the contribution, I should say, from the bottom face. So that's rho v y minus delta y over 2. So now, all this is saying is that we're going to approximate these integrals as just the face area times the quantity rho times u, or rho times v, evaluated at the midpoint. Now, so this seems to be, if we put everything together, that we're at a bit of a standstill. So putting everything together, if we do that, we get delta x, delta y, times partial rho, partial t, which this is just the volume integral term, plus this contribution over here. And this whole thing is equal to 0. So, and I'll put that as x. So as of right now, it looks like we can't do much more with this. But now we're going to take advantage of the fact that, again, the control volume is of infinitesimal in size. So we need to link any quantity that is at the edge of the control volume to the value at the center of the control volume. So to do that, let's recall the Taylor series. And so if we have f at, say, x plus delta x, I'll do that over 2, this is equal to f at evaluated at x plus delta x over 2, and that's equal to f evaluated at x plus delta x over 1 factorial times partial f partial x plus delta x, delta x over 2 times 1 factorial plus delta x squared over 2 squared times 2 factorial partial squared f partial x squared plus, and so on and so forth. So I will just write this as this equals to f plus delta x over 2 partial f partial x plus delta x squared over 8 times higher order terms. Okay, so our HOT. Okay, so now we're going to apply this to rho u and rho v. So applying this Taylor series, we have rho u at x plus and minus delta x over 2. I'm just going to do both at the same time. This equals rho u plus minus delta x over 2 partial f partial x plus delta x squared over 8 times higher order terms. Okay. And for rho v at y plus minus delta y over 2, that equals rho v plus minus delta y over 2 partial f partial y plus delta y squared over 8 times higher order terms. Okay, so now we're going to take these two expressions here and we're going to substitute them into this expression over here. Okay, so now doing that, we get delta x, delta y, partial rho, partial t, plus the contribution from the y face, so this would be, or the right face, so this would be the area, which should be delta y, times rho u plus delta x over 2, partial f, partial x, plus delta x squared over 2 times higher order terms. Plus the contribution from the left face, so that's delta y, times rho u, minus delta x over 2 partial f, partial x, plus delta x squared over, this is not over 2, this is over 8 times higher order terms, plus the contribution from the top face, so that's plus delta x times rho v minus delta y over 2, plus partial f, partial y, plus delta y squared over 8 times higher order terms. minus, minus delta x rho v minus delta y over 2 partial f partial y plus delta y squared over 8 times higher order terms. And this whole thing is equal to 0. So now it just looks like we took a mess and substituted in and used the Taylor series to just make a bigger mess. But this is actually kind of nice, because first notice that we have a plus delta y rho u here and a minus delta y rho u here. So those two terms cancel out, and similar for the v. And notice we have plus delta x over 2 partial f partial x, and we have minus delta x over 2 partial f partial x. So these two terms combine to form delta x partial f partial x. And similar for the y terms, these two terms combine to form delta y partial f partial y. Okay, and in general, these higher order terms don't cancel out, even though they look like they're equal and opposite, they aren't, because there could be third order terms, fourth order terms, fifth order terms, etc. So I'm just going to leave them alone. Okay, and pretend that they don't cancel out, because in reality they don't. Okay, so now simplifying this, we have delta x, delta y, partial rho, partial t, plus delta x, delta y, partial rho u, partial x, plus delta x, delta y, partial rho v, partial y, plus delta y, delta x, times delta x squared, not delta x squared, just delta x, times higher order terms, plus delta y times different higher order terms. And this whole thing is equal to 0. Okay, since this whole thing is equal to 0, and every single term is multiplied by the same delta x, delta y, I can just drop these out. Okay, and so we are left with partial rho, partial t, plus partial rho u, partial x, plus partial rho v, partial y, plus delta x times some higher order terms, plus delta y times some higher order terms, and that's equal to 0. So now, we have not invoked our assumption that the control volume is infinitesimal in size. So now what we're going to do is take the limit as delta x approaches 0 and delta y approaches 0 of this expression here. Okay, and if we do that, the only two terms that are multiplied by delta x and delta y are these higher order terms, and so those go to 0 because delta x approaches 0 and delta y approaches 0. So what we are finally left with at the end of the day is partial rho, partial t, plus partial rho u, partial x, plus partial rho v, partial y, equals 0. And so this is conservation of mass, aka continuity, for the 2D Cartesian coordinates. Okay, and the reason it's 2D Cartesian coordinates is because our control volume looked like a square, and we only considered it in 2 dimensions. In 3D, this becomes partial rho, partial t, plus partial rho u, partial x, plus partial rho v, partial y, plus partial rho w partial z equals 0. And so this is continuity in 3D Cartesian. Okay. And you can derive this the same way. You can use an infinitesimal control volume, but instead of looking like a square, it'll look like a cube. And you just got to keep track of everything. And it's largely the same, it's just a lot more bookkeeping. Okay? But, so what do you do about other coordinate systems? It's not uncommon that you'd want to work in cylindrical coordinate systems. Like if you're doing pipe flow, it'd be very natural to work in cylindrical coordinate systems rather than a Cartesian coordinate system. So what do you do about that? Well, in general, we have partial rho, partial t, plus the divergence of rho v equals 0. And this is any coordinate system. Okay, and you just have to look up in your math textbooks what the operator for a particular coordinate system, say cylindrical coordinates, what the divergence operator is, and apply that consistently. And so physically, this term represents the accumulation of mass as a function of time, and this is the net mass flux out of an infinitesimal control volume. Okay? And so, and where this general form comes from, it's actually a very quick and elegant derivation. And so I'll do that because it takes about 3 lines. But you do need to be comfortable with your calculus 3. And so as a primer, we're going to recall the divergence theorem, which states that the surface integral of b dot n hat of a vector b dot n hat dA is equal to the volume integral of the divergence of b dv. And so we're going to apply this Gauss divergence theorem to our integral form of the conservation of mass. And so we have partial t of the volume integral of rho dv plus the surface integral of rho v dot n hat dA is equal to 0. So applying the Gauss divergence theorem, this is equal to the volume integral of the divergence of the vector rho v, because again, that's the quantity that we're multiplying or that we're dotting with n hat. So rho v dv. So we're going to make that substitution and see what we get. But before we do that, we're going to make the assumption that the CV is not deforming. And that means its volume is not changing. And so because the CV is not deforming, we can interchange the volume integral operator and the partial and the time derivative operator, so we can move that in, but only because the CV is not deforming. And so when we do that, this term then is equal to the integral over the control volume of partial rho, partial t, dv. And again, we can only do this because we're assuming the control volume is not deforming. Okay, so we then set this equal to the integral of the, not equal to, plus the integral over the control volume of the divergence of rho v dv is equal to 0. Well, we now have two integrals that are over the exact same bounds. We can combine them. This equals the volume integral of partial rho, partial t, plus the divergence of rho of v over the volume is equal to 0. Well, in general, it's kind of trivial. We can always make this true by choosing a volume that has no volume, but that's not what we're after here. So the only way in general to make this true is to force the integrand to always be equal to 0. So the integrand must be 0 to make this true. Which implies that partial rho, partial t, plus the divergence of rho v equals 0. Okay, and so that's how we derive the conservation of mass in general using the Gauss divergence theorem. And again, it's if you're comfortable with your Calc 3, this is a much more fast and, quite frankly, easy way to do it. But you can't always use this, as I'll show later on an example where we derive some governing equations for pipe flow in one dimension. Okay, and so next time I will continue on with the substantial derivative, and we will work with this continuity equation a bit more. So that's it.